Welcome to 5-6 class. Today we get to start probably what I consider my favorite section of this chapter. We are going to move into the fundamental theorem of of algebra. And what we're going to be talking about is how to apply this to find all of the roots, real and imaginary, of a given polynomial. To begin that, we are going to start with the rational root theorem. What the rational root theorem says is any possible rational root, again rational meaning fraction of two integers, so any rational root of a polynomial will be the factors of the constant term divided by the factors of the leading coefficient. Or more visually, we're talking about this. The possible rational roots are the factors of the constant term divided by the factors of the leading coefficient. Now, again, this probably doesn't mean much to showing you the words, so let's show you how to actually apply this. So, in that first example, 2x cubed minus x squared plus 2x plus 5. So, the factors of the constant term, the factors of 5, are plus or minus 1, plus or minus 5. The factors of the leading coefficient. Now, what the leading coefficient is, the coefficient of the term of the highest degree. So in all these polynomials we're talking about, when we write them in standard form, the leading coefficient is that first coefficient. So in this case, 2. The factors of 2 are 1 and 2. So what this is telling us is it gives us a way to find the possible rational roots, which they've listed right here. And if you notice, what they did is they divided each of the factors by 5 by a factor of 2. So 1 divided by 1 gave us the 1, 5 divided by 1 gave us the 5, 1 divided by 2 gave us the 1/2, and 5 divided by 2 gave us the 5/2. Okay? So once we have those are the possible rational roots. So if we're just looking for what the rational roots are, all you'd really have to do at that point is test out every one of those values and see for which one is the polynomial 0. So in this case, in this polynomial, if we're looking for a rational root, you can see this polynomial has one rational root, and it is where x is -1. Now, I'm going to take this a step further. So instead of just having you look to see, okay, what's a rational root? I'm going to discuss how can we use this information to find every root of a polynomial. Now, before we dive into that, something else we need to understand is the fundamental theorem of algebra. What the fundamental theorem of algebra says is if p and x is a polynomial of degree with greater than 1, then p of x equals 0 has exactly n roots, including multiple and complex roots. So what this means is whenever we're dealing with a quadratic, degree 2, then that means we're always looking for 2 roots. Cubic will always have 3 roots, so on and so forth. Now these roots can look different, however. So look at the 3 graphs that I've put on the bottom for you. So we're dealing with the quadratic there, so we know we are absolutely looking for 2 roots, always. However, they can present themselves differently. In the first one, to the left, y equals x squared minus 4, you have 2 real zeros. That's what we like to see. That's the easiest one to see, that you can have as many solutions as the degree. However, look at the middle one. Y equals x squared minus 2x plus 1. This one looks like it only has one solution. However, if you take into effect that that solution is a multiplicity of 2, you can see that is where your 2 solutions come in, because your single solution has a multiplicity of 2, so it actually counts as 2 solutions. Then the one on the right, y equals x squared plus 2x plus 2, that has no real zeros. So what that is saying is you have 2 complex roots, but nonetheless you're still dealing with 2 roots. So again, essentially what this is saying is no matter what, you are always going to have the same number of roots as you do the degree of the polynomial. So now that we've discussed that, let's move on to an example to see what am I really talking about here. So, finding all the roots of a polynomial, I've broken this down into a systematic set of steps for you to follow. So, the first thing I want you to do, use the fundamental theorem of algebra to decide how many roots you are looking for. So, if this is the polynomial that we are looking for the roots for, you can see the fundamental theorem of algebra says we are looking for 5 roots. Okay, you look at the degree of the polynomial to tell you how many roots are you searching for. In this case, we're searching for 5. Use a rational roots theorem to determine the possible rational roots. All right, so we take the roots of the constant. So here, plus or minus 1, plus or minus 2, plus or minus 4 are the roots of the constant. Then here, roots of the leading coefficient, well in this case it's 1, so the roots are just plus or minus 1. So that means the possible rational roots. Well, if for each of these we're just dividing by that plus or minus 1, really all we get is that same list from the factors of the constant. But that's going to give us a place to start our search. Now, the next thing we're going to do, use a graphing calculator to identify a true rational root and begin using synthetic division. All right, so what we're going to do is pull out our graphing calculators because we're going to graph this equation because that's going to give us our starting point to searching to find all of the roots. So I call up my graphing calculator and I'm going to plot that x to the 5 minus x to the 4 minus 3x cubed plus 3x squared minus 4x plus 4. So it's a little beastly to type in. Now, the calculator doesn't have any special way to represent exponents greater than 3. So I actually have to put in x to the 5th power like that minus x to the 4th power minus 3x to the 3rd power plus 3x squared, 3x squared minus 4x plus, plus 4. And we're going to graph this. All right, so here is our equation, or here's our graph. And again, the point here is to begin identifying where are our real roots so we can use synthetic division to break this down. So I see a real root back here at -2, all right? So that's actually where I'm going to start my synthetic division, is at -2. So once I found one, I'm going to use synthetic division beginning at that -2. So 1x to the 5th minus 1x to the 4 minus 3x squared, or x to the 3, plus 3x squared minus 4x plus 4. So I set up my synthetic division, and now I'm actually going to carry it out. So I carry down the 1, multiply by the -2. -1 plus -2 is a negative 3. Multiply by the negative 2. Add, multiply by the negative 2. Add, multiply by the negative 2. Add, multiply by the negative 2, and add. So, looking at this, remember, this is telling us our remainder, our constant, our x term, our x squared term, our x cubed term, x to the 4, so on and so forth, if there were more terms. So, what we've done here is really broken this down, because now we know one of our roots was at 2. So I'm going to put that up here. One of our actual roots, I'm sorry, not 2, was at negative 2. All right, and so what this has given us is now a new polynomial. Okay, once we broke this down, now we factored out the factor of x plus 2. And now we have left x to the 4 minus 3x cubed plus 3x squared minus 3x plus 2. All right, so we factored out a piece of our polynomial, okay? So now all we have to do is go back, and we can do this process again with a new 0. So let's take a look. I'm going to go back to my graph and say, all right, I also have a root at 1. So now that I've identified it, I have another root at 1. I'm going to use synthetic division, but this time on just the piece of the polynomial that I have left. All right, so 1x to the 4, negative 3x cubed, 3x squared minus 3x plus 2. I'm only going to use it on the portion that is remaining from the first synthetic division. And now we're going to do our process again. Pull down the 1, then multiply by 1. Add, multiply by 1. Add, multiply by 1. Put over here. Add, multiply by 1. Add. So this is what we have remaining. So here's our remainder, our constant, x term, x squared term, x cubed term. So now we've actually broken this down further. So now this piece right here, we've broken out an x minus 1. And now what we have left is an x cubed minus 2x squared plus x minus 2. So now that we have that, and we can add in our list of roots, we have a 1 there. Now we're going to go back and we're going to check for our next root to continue breaking this down, because that's our goal. We're going to break this all the way down till we have all of our roots. Well, if I look at my calculator, I see another root at positive 2. So I'm going to do positive 2 now. And again, I only have to use synthetic division on the polynomial I have left. So 1x cubed minus 2x squared plus 1x minus 2. So pull down the 1, multiply by 2, add, multiply by 2, add, multiply by 2, and we're done. Remainder are constant, x and x squared. So now I've broken out another root because I have remainder 0. So now I have a new factor of x minus 2 because we have another real root at 2. And now we have left x squared plus 1 because there's no x term this time. So now looking at this, we've worked our way all the way down, so we have a quadratic left. All right. Now, that's kind of our goal here because quadratics we know what to do with. Quadratics we can actually solve. Because now, if I still have that quadratic piece and I want to find its root, can't I just set it equal to 0? And this one is particularly easy because we can solve this just by square rooting. I can subtract that 1 over. I can square root both sides now. And the square root of negative 1 is I. So we're getting plus and minus I. So now with that addition, you can see we have found all 5 of our roots. Look, we have plus and minus 2, we have 1, and we have plus or minus I. By using the synthetic process, we have found every root, all 5 of them. Now, I apologize that this is getting to be a little bit lengthier of a video. However, I do still want to do one more example with you. All right? So, just to make sure that we're getting the hang of this, let's do one more example. So, by the fundamental theorem of calculus, or of algebra, when we're looking at this one, we know we're looking for 4 roots because that is a degree of the polynomial. Now, the possible rational roots. Well, we take all the factors of 6 and we divide them by all the factors of the leading coefficient. So this is another simple case because when we're only dividing by plus or minus 1, basically we're just recreating the list over there. Now, I'm going to use my calculator. I'm going to start searching for real zeros. So I'm going to pull up my calculator. Now, I need to go back, clear out the graph that I was just doing, and start fresh. So, x to the 4 plus x cubed minus 7x squared minus x plus 6. So, I'm going to use a synthetic division to find and verify the 4 roots. So notice I have one back at negative 3. So, I'm going to break this down. At negative 3, I'm going to use my synthetic division. So, 1x to the 4, 1x cubed, negative 7x squared, minus 1x plus 6. So, bring down the 1, multiply by negative 3. Add, multiply by negative 3. Add, multiply by negative 3. Add, multiply by -3, and add. So you can see it did turn out to be a true root. So we have our remainder here, constant here, x, x squared, x cubed, so on and so forth. So we have a real root at -3, so I'm going to put that up here to begin my list. And what this means is we have a linear factor of x plus 3, and what's left is an x cubed minus 2x squared minus x plus 2. So I've broken down my first chunk of this polynomial. Now let's see here. Looks like we have another root at -1. So I'm going to use this process on my new polynomial that I have left at -1 to verify that one. So 1x cubed minus 2x squared minus 1x, oh, then positive 2. Let's see what happens here. Pull down my 1, multiply. Add, multiply by -1. Add, multiply by -1, add, boom. All right, so remainder, which was 0 again, which is what we're looking for. Constant, x, x squared. So we can add -1 to our definite list of zeros. And now this broke down again. We have a linear piece now of x plus 1. Now we have x squared minus 3x plus 2 left. Now notice, remember when I said this was our goal? Now we have a quadratic left. And by having a quadratic left, now we should be able to solve this in another way. In this case, that x squared minus 3x plus 2, if we have that set equal to 0 to be finding the roots, well, this actually factors. Okay, so you could keep using the synthetic process on this one because it actually has all real roots. However, if you wanted to factor this instead to prove the roots, that will work just as easily. Because if you look at the graph, you'll see you have another root at 1 and another root at 2, just like the factoring told us. So now we have found all 4 roots. And again, I apologize that this video got a little bit longer, but it is all essential information, okay? This is kind of the accumulation where this entire chapter has been heading, is finding every zero, real and complex. So please make sure you have all of this written down, and then please make sure you bring this back to class so we can do our practice work. And I'm sorry, I actually just realized I left a little bit on the bottom for us to discuss, just to review. So, name based on degree. This is something we should be able to do of any polynomial now. This is a quartic function. Name based on number of terms. Well, it's a polynomial of 5 terms. Remember, once you get above 3, there's no special name anymore. And then the end behavior. If you remember the graph, it goes up in both directions. So both times it's going to infinity. Again, sorry for nearly forgetting that. So, but again, please make sure you have all this written down. Come back to class prepared to do our practice work.